So what happens at resonance is Z becomes equal to Ra plus Rb because there is no XL and XC. What happens is that there is no XL and XC. Since there is no XL and XC, because the condition is of resonance, Z is equal to Ra plus Rb. Therefore, the input impedance is purely resistive and minimum. So the input current and output current, input voltage and output current are in phase. What is the input current? What is the input voltage? Input voltage is V1, and what is the output current? The output current is I, isn't it? This is the output current I, and the input voltage is V1. So from this itself, since the condition is resonance, we can conclude that the input voltage V1 and the output current I are in phase. So we are going to check in which of the following diagrams V1 and I, the input voltage V1 and the output current I are in phase. We will have to check. So here V1 is not in phase with I. Here also V1 is not in phase with I. Here also V1 is not in phase with I. Here V1 is in phase with I. So what is our option? Our option is option A. So the phasor diagram which is applicable to this circuit under condition of resonance is option A. So actually there is no need of doing this much of problematic part, because when the condition is given as resonance, you have to always remember that the voltage and the current are in phase. So you will have to check for the initial check of the diagram in which the voltage and the current are acting in phase. So from that itself you will be able to see that the voltages and the currents are in phase for option A only. So we will have to go with option A. Now moving into question number 39. An energy meter is connected to an immersion heater operating on an AC 230 volt 50 Hz single phase source, and it reads 2.3 units in 1 hour. The heater is removed from the supply and now connected to a 400 volt peak to peak square wave source of 150 Hz. The power in kW dissipated by the heater will be, is the question. So first, an energy meter was connected to an immersion heater operating at AC 230 volt 50 Hz single phase source, and it reads 2.3 kilowatts. The heater is removed and then connected to a 400 volt peak to peak square wave source with 150 Hz. The power dissipated by the heater for the second case is to be found out. Now assuming that the resistance of the heater is R, in condition 1, the heater is connected to 230 volt 50 Hz source which is an AC source, and then the energy consumed is 2.3 units or 2.3 kilowatt hour in 1 hour. Now power consumed by the heater is what? The power consumed by the heater is energy divided by time period. Energy by time period. What is our energy? Our energy is 2.3 kWh. Time period is 1 hour. So what is power? Power is 2.3. Power consumed by the heater is 2.3 kW. Now the RMS value of the input voltage is given as 230. So Vrms is equal to 230. P is equal to Vrms square divided by R. We have obtained P. From this we will be able to find out the value of the resistance of the heater, resistance of the heating element of the heater, as R is equal to 23 ohms. Now this 23 ohms we will have to put it into the next condition. Now the heater is connected to a 400 volt peak to peak. So that means it goes from plus 200 to minus 200 square wave, and its frequency is 1 by time period. The time period is equal to, the frequency is 150 Hz. So the square wave frequency is 150 Hz. So what we are going to do is that we are going to find out the RMS value as 1 by t integral 0 to t v square dt the whole raised to 1 by 2, and then from this you will obtain as Vrms is equal to 200 volt. Okay. Now what is the power? Power is equal to Vrms square divided by R. R we already know that R is 23 ohms. So what is our new Vrms? New Vrms is 200. So it is 200 square divided by 23 into 10 raised to minus 3 kW. So it consumes 1.739 kW. This is a good question, an extremely good question because it carries two aspects. One in the sinusoidal format, second one in the square wave format. So a portion of this question can also be asked for the upcoming examinations. So what is our answer? Our answer is 1.739, which is choice B, and this is a 2006 question for 2 marks. So it is B is equal to 1.739 kW kilowatt unit. So it is kWh is what is our answer. Now the state equation for the current for question number 40. I1 shown in the network shown below in terms of the voltage V of x, in terms of the voltage V of x and the independent source V1 is given by, independent source V1 is given by. So the state equation, we have to find out the state equation for the current I1. State equation for the current I1 shown in the network shown below in terms of the voltage Vx and the independent source V1 is given by, is what is the question. So we are going to find out the state equation. So any state equation represents the dynamic behavior of the given electrical network. State equations usually follow a specific format while being represented. On the left side of each state equation, the derivative of one variable is used. On the right hand side, a mathematical function is represented involving any or all the state variables and the sources. So this is the format in which the state equation of a system or a given circuit is made. So we have recreated the same diagram. So this is our diagram and we are going to apply Kirchhoff's voltage law in loop 1, and this is voltage V. So voltage V minus 3 into what is current passing through 3, it is I1 plus I2. Here the current is I2 and here it is I1. So we are assuming that the current is branching into I1 and I2 and the total current is I1 plus I2. So it is V minus 3 into I1 plus I2 minus Vx minus 0.5 di1 by dt is equal to 0 becomes equation number 1. And we are going to make loop equation in the second loop also. So it is 0.5 di1 by dt plus 5 minus 5 I2, this is minus 5 I2, then plus 0.2 V of x is equal to 0. So this is equation number 1 and equation number 2, and we are going to eliminate I2. We are going to eliminate I2 from equation number 1 and equation number 2. So we are eliminating I2 from equation number 1 and equation number 2. And when you are eliminating I2 from 1 and 2, because it is 5 I2 and here it becomes minus 3 I2. So you have to eliminate I2 from equation 1 and 2. Then we will get an expression of di1 by dt. Of di1 by dt, because di1 by dt is present in both the equations. And you will have to make the equation in a format of di by dt, because our choice is given as di1 by dt minus of. So make an equation as di1 by dt is equal to, you will get it as minus 1.4 V of x minus 3.75 I1 plus 5 by 4 V equals di1 by dt. So what is our answer choice? Our answer choice is di1 by dt minus 1.4 Vx minus 3.75 I1 plus 5 by 4 volt, isn't it? Plus 5 by 4 volt. So it is minus 1.4 Vx minus 3.75 I1 plus 5 by 4 V is equal to, this is our equation. Okay, so this is option A. Our answer is option A. So di1 by dt is equal to, this is actually equal to, so di1 by dt is equal to minus 1. Vx minus 3.75 plus 5.4 is equal to 0. Okay, so di1 by dt minus 1.4 Vx minus 375 I1. So you have to make it like, you have to make it in this form. So di1 by dt is equal to, eliminating di1 by dt, eliminating I2 from equations 1 and 2, we will be getting di1 by dt is equal to minus 1.4 V of x minus 3.75 I1 plus 5 by 4 V, which comes to be option A. So option A will be the answer. So you will have to do it by yourself and you will have to find the conclusion of the equation. Okay. So it's only mathematical. When you solve this, you will be getting this expression. So question number 41. We are continuing with the question 41. So in the figure given below, all phases are with reference to the potential at point O. The locus of voltage phasor Vyx as R is varied from 0 to infinity. So here also we are varying R from 0 to infinity. In the figure given below, all phasors are with respect to the potential at point O. Okay. The locus of voltage phasor Vyx as R is varied from 0 to infinity is shown by is what is the question. So 4 choices are given, A, B, C and D. We will have to find out which is the correct answer. Now we have redrawn the figure. This is the voltage Vyx and this is the variable resistance R. Here we are having AC voltage sources V angle 0 and there is a capacitance C. So now we are going to find out. Now we have to find out the locus of the voltage phasor Vyx. So we will have to make an equation for Vyx. Now let us assume that the capacitor reactance of C is Xc. So we are going to make an equation for I. What is an equation for I? An equation for I is V angle 0 plus V angle 0, the net voltage divided by net impedance. What is net impedance? Net impedance is R minus jXc. So here it becomes 2V divided by R minus jXc. Now when we are using Kirchhoff's law in the first loop, we can say Vyx plus IR minus V is equal to 0 in the upper loop. From this we can write Vyx is equal to V minus IR. And we have obtained an equation for I, isn't it? So we can substitute this I into this equation. So it becomes Vyx is equal to V minus I into R. And then you will have to reduce the equation such that we will get a final expression for Vyx equals minus V into R plus jXc divided by R minus jXc. Now we are varying R from 0 to infinity. R is varied from 0 to infinity. So we are going to substitute first case R is equal to 0. When you are substituting R is equal to 0, you will get an expression for Vyx. And then you substitute R is equal to infinity, then we will get it as Vyx is equal to minus V. So these are our two values. Our first value is that when it is R is equal to 0, Vyx is equal to minus V into R plus jXc by R divided by 1 minus jXc divided by R. When R tends to infinity, Vyx becomes equal to minus V. So with this we will have to check which of the following is answer. Here when R tends to infinity, Vyx becomes equal to minus V. So here you have to see that both our expressions are negative. Both expressions are negative. Since both expressions are negative, we cannot have a positive locus. So that means this and this cannot come. Only a negative locus is possible. And here it depicts 0 to 2V and here also it depicts 0 to 2V. But here the locus is at V and here the locus is at 0. It starts at 0. The origin is at 0. So our value is actually when Vyx when R tends to infinity is minus V. Here it is not possible for us to obtain minus V because it goes from 0 to 2V. So our answer has to be option A because here we can go to minus V and also to 2V. So it can shift from 0 to 2V. So that means a V possibility is there. But here only a possibility of 2V is there because the radius of which the phasor is working is that it goes to from 0 to 2V. So here our division factor is V because it is from 0 to V and then from V to 2V. So we will conclude with option A for question number 41. Now moving into question number 42, a 3 volt DC supply with an internal resistance of 2 ohm supplies a passive nonlinear resistance characterized by the relationship VNL equals I square NL. The power dissipated in the nonlinear resistor is to be found out. So we are drawing the diagram. We are having a DC supply. There is a resistance which is the internal resistance of the battery then there is a nonlinear load. And the equation that they have given is that VNL equal to I square NL. Okay, so VNL is equal to I square NL. So from this diagram, we can make an expression for VNL as VNL is equal to E minus I NL into R. V minus INL into R. So E is given that the battery is having a voltage of 3 volt. So we can substitute E is equal to 3, and what is the value of resistance? The resistance, internal resistance is 2 ohm. So you can substitute internal resistance also. So we will get the expression as VNL equal to 3 minus 2 INL, which is also equal to INL square. Okay. From this you will be able to make a quadratic equation and isolate the value of INL square. So INL square either becomes minus 3 ampere or it becomes 1 ampere. Now minus 3 ampere is rejected because nonlinear resistance is passive and the only active element in the circuit is 3 volt DC supply. So the current cannot be negative, which is supplying the power to the resistor. So there is no absorption, there is only supply. So minus 3 ampere is not positive, and it is not possible. Minus 3 ampere is not possible. So we will have to conclude with I square NL is equal to 1 ampere. So we conclude I or NL is equal to 1 ampere or INL is equal to 1 ampere. Now when you are going into finding the power dissipation, what is power dissipation? It is VI or it is I square R. It is I square R. It is I square R, but we cannot take it as I square R. We are going to substitute for VNL. What is VNL? VNL is equal to INL square. So VNL can be substituted to INL square into INL, which is actually INL cube. So it is 1 cube or it is 1 watts. So what is our answer? Our answer is option A, which is 1 watt. So this is answer for question number 42. Now moving into question number 43. The Thevenin equivalent of a circuit operating at omega equals 5 radians per second has the open circuit voltage as 3.71 angle minus 15.9 volt and impedance as 2.38 minus j 0.667 ohm. At this frequency, the minimal realization of the Thevenin impedance will have A is what is the question. So the Thevenin's equivalent of a circuit operating at omega equal to 5 radians per second has open circuit voltage 3.71 angle minus 15.9 degree volt and Z0 is equal to 2.38 minus j 0.667. So this is what is our arrangement that is given, and the minimal realization of the Thevenin impedance is what is the question. So we are just writing down the details that is given. So the Thevenin impedance is this. So here you have to understand that the imaginary part is negative. Imaginary part is negative means imaginary part is predominantly capacitive. Okay, so that means XL minus XC is predominantly XC. As a real part is not 0. So since the real part is there, we must have a resistor. Okay. And the imaginary part is minus j 0.667. So the case 1, since it is negative, it must have a capacitance. Okay. Case 2, it will have both capacitor and inductor, but XL value will be lesser compared to capacitive reactance. Now at omega equal to 5 radians per second, for minimal realization, we will have to go with the case 1. Okay. Because you see, when omega is equal to 5 radians per second, what is our XC? XC is equal to 1 by omega C. And what is XL? XL is equal to omega L. Okay. So that means when omega is having a lesser value, this denominator, here the omega go into the denominator and here omega is in the numerator. So it is directly proportional to omega and here it is inversely proportional to omega. So we are going to go for a minimal realization. Minimal realization means we have to go for minimum elements. Minimum elements means the possible elements are R, L and C. Okay. Since we have a real part, we have to go with the resistance. The imaginary part is negative, that means the capacitance is strictly there. So with the minimal realization means there is no a need of an inductor, because if it is a maximal realization, then it is inductance and capacitance with the resistor, where capacitive reactance is greater than inductive reactance. But since it is a minimal realization, we will go with a resistor and a capacitor. We will not include an inductor, because inductor contributes positive imaginary part. Since our imaginary part is negative, we will go with a minimal realization of capacitor. Now for question number 44, assuming ideal elements in the circuit shown below, the voltage VAB, we will have to find the value of voltage VAB. So we are making equations for the circuit. Here we are having a 1 ampere source. Here it is 5 volt, and then there is a 2 ohm resistance. So we can make a loop equation as if I is equal to 1 ampere. I is equal to 1 ampere. So we are going to make a loop equation as VAO. This is VAO. This is VAB. This is VAB minus 2I plus 5 is equal to 0. So VAB, this is Kirchhoff's voltage law equation made in this loop. Okay. So VAB minus 2I plus 5 volt is equal to 0. And from this, you will be able to make an expression of VAB in terms of I. Okay. And we already know that I is equal to 1 ampere. Because I is given as 1 ampere, it is only a single series loop. So substituting I is equal to 1 ampere, you will get the value of VAB as minus 3 volt. Minus 3 volt is option A. So for question number 44, we will go with the option A. Now about question number 45. In the circuit shown in the figure, the value of the current I will be given by, is what is the question. So the circuit shown in the figure, the value of the current I will be given by. So this is I, this is current I. So we will have to find out the value of I. So we are redrawing the circuit and we are making equations for loop 1 and loop 2. So we are making equation in loop 1 as 5 minus I1 is equal to 0. So from this we will get an expression for I1 and the value of I1 as 2.5 amperes. Now I1 is equal to 2.5 amperes means 2.5 into 1 equal to VA. So that means VA is also equal to 2.5 volt. Because VA is the drop in 1 ohm. So the current is 2.5 amperes into resistance becomes VA. We are making equation for loop 2. 4 VAB equals 3I2 plus I2. So from this you can make an expression for I2 and you will get I2 is equal to 4 times VAB, because this is 3I2 plus I2. So it becomes 4 VAB divided by 4 is equal to VAB, or it is equal to 4 VAB. So this is VAB. Okay. So I2 is equal to VAB. Now VB, what is VB? VB is the voltage at this point. This is VB. This is VB. So what is VB? VB is equal to 1 into I2. It is 1 into I2, and this is exactly equal to and this is VB. Okay. So VB is equal to 1 into I2. So we can put it like VB is equal to 1 into I2. And then what is VBA? What is VBA? It is VA minus VB, or you can say VAB is equal to VA minus VB. It is the difference between A and B. Okay, so the voltage difference between A and B. So it becomes VA minus VB. And what is VB? VB in the question, it is given in the circuit shown in the figure, the value of current I. We will have to find this value of I. Okay, and we are going to make an expression in terms of the dependent source. So the dependent source is actually 4 VAB plus 3I2 plus I2. So from isolating I2, it becomes 4 VAB divided by 4, or it becomes equal to VAB. So from this we have got a valuable expression like I2 is equal to VAB. I2 is equal to VAB. So I2 is equal to VAB. So that means in for I2 we can substitute VAB. So when substituting I2 is equal to VAB, what is VB? VB becomes equal to VAB. Okay, VB becomes equal to VAB. So when VB is equal to VAB, What is VAB? VAB is VA minus VB. Okay. So we can also write VB is equal to VA minus VB. VA minus VB. Or you can say 2VB is equal to VA, or VB is equal to VA divided by 2. And what is the value of VA that we obtained? It is 2.5. So dividing 2.5 divided by 2, what is our VB? VB is equal to 1.25. And you have obtained VB. So from this you will be able to obtain VAB, isn't it? So we have obtained VB. VB is equal to what? VB is equal to VAB. So 1.25 is exactly equal to VAB, and you can reversibly see VAB is equal to I2. So what is I2? I2 is also 1.25. I2 is also 1.25. So what is our answer? Our answer is option B, which is 1.25 amperes. So that is about question number 45. So these are some important questions where the relationships matters the most. How you make the equation leads you to the answer. If you are going to make any step mistake, then you will not be getting the answer. So the variables are mixed up such that you will have to go for a keen attention in making the equation. So you have to practice this many times for making the final expressions. Now for question number 46, the current through the 2 kilo ohm resistance in the circuit shown is, what is the question? Current through the 2 kilo ohm resistance in the circuit. Now this is the 2 kilo ohm resistance in the circuit. So it is a 6 volt source. There is 1 kilo ohm, 1 kilo ohm, 1 kilo ohm, 1 kilo ohm bridge is there. Okay. Now this is a balanced bridge. Therefore no current flows through the 2 kilo ohm resistor. This is like a balanced bridge. So it is 1-1-1-1 arrangement. So it is a balanced condition. So no current will be flowing through the 2 kilo ohm resistance. So what is our answer? Our answer is option A, which is 0 milliampere. So it is option A, 0 milliampere. Going into question number 47, how many 200 watt 220 volt incandescent lamps are connected in series? Connected in series would consume the same total power as a single 100 watt 220 volt incandescent lamp. So this is 2009 1 mark question. So we are going to connect incandescent lamps in series. So we must know how many 200 watt 220 volt incandescent lamps. 220 volt doesn't matter because it is common. So how many 200 watt incandescent lamps connected in series would consume the same total power as a single 100 watt incandescent lamp? So let the resistance of the single incandescent lamp is R. Power consumed by the single lamp is 200 watts. Okay, the first case, the power consumed by the lamp is 200 watts. And when it is connected to 220 volt. Okay, so what is P? P is equal to V square divided by R. Our P is equal to 200. V square is 220 square divided by R. Resistance of the filament, we get it as 242 ohm. So let n number of lamps are connected in series. Okay, voltage V is equal to 200 volt. Okay, so the total resistance of the lamp will be, if n lamps are connected in series, the total resistance will be n times R, isn't it? So it is 242 into n. So the total power consumed is now P is equal to V square divided by R equivalent. V square divided by R equivalent is n times 242. Okay, so what is P? The second case, P is 1000, voltage is still 220. So not 1000, it is 100. So P is equal to 100, voltage is 220 square, and R equivalent is n times 242. So when you are cancelling this, you see n is equal to 2. So 2 lamps has to be connected in series. Two 200 watt lamps has to be connected in series to consume the same power of a single 100 watt lamp. So what is our option? Our option is option D, which is 2. Question number 48. The equivalent capacitance of the input loop of the circuit shown is what is the question. So this is the input loop. It is already indicated in the question. The equivalent capacitance of the input loop of the circuit is to be found out. Here you can see in the input loop there is 1 kilo ohm resistance and there is another 1 kilo ohm resistance. There is 100 microfarad capacitance. So we are going to find out the equivalent capacitance in the input loop of the circuit. So we have recreated the circuit and we are going to apply Kirchhoff's voltage law into the first loop. So that means V in minus I1 into 1 plus 1 minus 50 I1 into minus jXC is equal to 0. Okay. So we will have to reduce this for IN is equal to I into 2 minus j50 XC. So Vn is equal to, this is our expression, Vn is equal to, so this becomes equal to 2 I1 minus 50 I1 minus 50 jXC I1, isn't it? So we can take I1 as common. So when you are going to convert this, this is going to become like this is Vn, this is not In, this is actually Vn. Okay. So Vn is equal to, this will become positive on this side. So I1 can be taken as common. Then in the bracket you will have 2 minus j50 into Xc. So this is our Vin. Okay. And we will have to find out the input impedance. What is input impedance? What is input impedance? Zn, it is Vin divided by In. It is Vin divided by In. So you can take I1 here. So Vin by In becomes equal to minus, it is 2 minus j50 Xc. Now the imaginary part is negative and there is only capacitance. There is no inductance in the first loop. There is only capacitance. So what is the reactance? The reactance can be directly taken to be 50 Xc. Okay. So when reactance is 50 Xc, then 1 divided by omega C equivalent is equal to 50 divided by omega C, and from this we can find that the C equivalent is equal to 2, capacitive equivalent is equal to 2 microfarad. So 2 microfarad is the equivalent capacitance of the input loop that we can see from the opening side of the circuit. So what is our answer? Our answer is option A, which is 2 microfarad. 2 microfarad is the net equivalent capacitance of the input circuit of this circuit shown in the figure. Now this is about question number 48. Now we are going to move into question number 49.